come in a variety of forms. They can be tall or short, long or compressed, and can vibrate quickly or slowly. We've seen that waves come from vibrations and can be very complex structures. In this program, we're going to look at the characteristics of a particular type of wave, the sine wave. It's produced when vibrations are very regular and smooth. Sine waves are important to measure because all waves...
Please stand by. We are having technical difficulties.
Hey, Rick, you down there? We lost a picture again here.
When a problem occurs in broadcasting, like the one you're just seeing, hold on a second. Yeah?
Rick, can you hear me?
Right. Yeah, I know. Well, I can't work on it if I'm talking on the phone, though. Okay.
Rick, we've lost the picture.
When a problem occurs like the one you just saw, some engineer somewhere who was minding his own business and drinking his coffee is running around. This equipment is very complex, but basically it all processes sine waves in one way or another. Every signal, audio or video or transmission, is made up of combinations of sine waves. In this particular case, what I'm particularly interested in is that this particular machine here puts out what I put into it. I'm going to use a test signal, which is defined as which is set up as series of sine waves. These sine waves change in frequency from 500,000 per second to a little over 4 million per second. It appears as a video signal, which you can see on your screen. It's also one that I can record and play back on the tape machine. The test in this case would be to make sure that what I get back off the tape is exactly what I put into it. There's a number of adjustments that can be made. This is what it looks like wrong, and this is what it looks like right. The idea is to get the two of them to match. And if I make a few magic adjustments here, like this, and this, now you can see that the input and the output match. Now we can go back to doing what we were doing before.
Okay, we got it back now. Thanks, Rick.
We now return to our regular program.
Sine waves are important to measure because all waves, no matter how complex, are made up of combinations of sine waves. Any regular vibration can set up sine waves, like the paddle on this wave tank. Water waves are almost pure sine waves. A floating object shows how the water is actually moving up and down, not in the direction of the wave. Only the energy moves in the direction of the wave. The particles are moving up and down. Amplitude is the height of the wave, and it's measured from a center line. This is where the water would be if there was no wave passing through it. The amplitude is the height from the center line to the top of the crest. Since the water also moves down during the wave cycle, you can measure amplitude as the depth of the trough. Amplitude measures the amount of energy in the wave. That's why surfers are interested in high amplitude waves. They want high energy rides. Wavelength is easy to measure if there's a train of waves. It's the distance between two crests. Or it can be the distance between two troughs. In fact, it can be the distance between any two parts of the wave that are in the same position. Amplitude and wavelength only tell you how big the wave is, but waves move from one place to another, often carrying a lot of energy. So it's important to describe the motion of a wave as well as its shape. There are two ways to measure motion. One way is to measure the number of waves that pass by a point in a period of time. The clock is counting seconds. The number is counting the number of times the wave completes a cycle. The number of cycles per second is the frequency. The frequency of this wave is about 1 cycle every second. Another way to measure motion is to measure how long it takes for just one wave to pass, the period. This wave takes about 0.9 seconds to complete one cycle. Period is seconds per cycle. You can see that frequency and period are the inverse of each other. If you know one, you can find the other. Changing frequency and period affects the wavelength, and this relationship enables you to calculate the velocity of the wave, either like this or like this. You will be dealing with this more in your text, but here's a little challenge. Can you calculate the frequency of a skyscraper as it blows in the wind? Listen to Doug Loesch, an engineer who has to measure the vibrations that pass through a tall building. Remember, frequency is the inverse of period.
Tall building like Columbia Center sways in the wind at its fundamental period of vibration. Columbia Center is very stiff building for its height, and those periods of vibration are in the range of 4 to 5 seconds. The period of vibration determines, to some degree, the accelerations and forces that the building experience, and we need to know these for design of the building, and also to determine if the occupants are going to be comfortable under those acceleration levels. To do this, it's much too complicated to apply conventional theory, so wind tunnel testing is employed. These two models were used in the actual wind tunnel testing at the University of Western Ontario in the design phase of Columbia Center. The model on the left is a static pressure model. It's solid plastic, and it does not flex much when the winds in the wind tunnel affect it. Surprising thing about Columbia Center is that it does not sway in the direction of the wind primarily. The most significant component of its vibration is transverse to the wind. And the reason for this is that as the wind blows on the building, its pressure as a function of time and position on the building is very irregular. And these fluctuations in pressure cause vortices to build up at the sides of the building. A vortex is like a whirlpool of wind, and periodically these vortices are shed from the side of the building, and when they're shed, they cause large suctions on the side of the building, which pull the building to and fro in the direction perpendicular to the wind. And thus the building vibrates at its fundamental natural frequency. The period of vibration of Columbia Center differs slightly in the north-south direction from that in the east-west direction, but they're around 5 seconds. There's also a period of vibration associated with twisting of the building, and that's in the 4-second range. In the maximum storm that the building could ever experience, the motion at the top would be a total of approximately 18 inches. Normal motions under normal winds are very small and cannot be perceived as rocking by the occupants.
The period of the building is 5 seconds per cycle, so the frequency is the inverse of that, 1/5 of a cycle per second. Sometimes there's more than one wave passing through a structure at the same time, and they need to be compared. When two waves are the same wavelength, frequency, and period, they are said to be in phase with each other. But if one of those waves changes slightly, their phase will shift according to how different the waves become. This is phase shift. Phase shift is important when trying to match signals from two different pieces of equipment. We have to do it when we're matching the tape recorders that put together this program. If our recorders are out of phase, the colors are wrong and the picture looks like this. In phase, it looks like this. The same is true in mechanical systems. Anytime two or more devices, like engines, vibrate at the same frequency, it's crucial that their vibrations be in phase. Otherwise, unnecessary beats and pulses appear that can do damage to the structure. You can hear this effect as extra beats that are appearing in these strings that are slightly out of phase. All these characteristics, amplitude, wavelength, frequency, period, and phase shift, also apply to compression waves like sound. The wavelength is the distance between two compressions. The frequency is the number of compressions that pass by a point in a unit of time, or cycles per second. And the period is the time it takes for one cycle to happen. And as we've already heard, two compression waves can experience a phase shift. Manipulating vibrations and waves is necessary in almost all technology. If they're not controlled, this is the result.
Okay, 1, 2, 3, go.
Boy, that was bad. Ooh.
Jeez. What happened? I don't know.